Alrighty. So today we're going to wrap up everything power series, every last detail, and then we're going to start conic sections. So I want to talk about a very specific type of problem. This is the last of the applications. And let's take something that we already know how to do. We know how to tweak. Okay, we know how to tweak. We know that e to the x, at this point, we probably know this. 1 over n factorial x to the n. And then if I wanted to tweak it, let's say I wanted, let's say x squared e to the x cubed. I want something like this. And then what I do is, whoops, I have the x squared here. And then I would put the x cubed to the n. And then that gives us something simple like this. That would be x to the 3n plus 2. Beautiful. Piece of cake. Going from statement to power series when it's a tweakage, particularly if it's an e to the x, if it's a geometric series, if it's a sine or cosine, it's probably a fairly simple matter. But what if I started with something like this? What if I started with the following power series? Let's see, which one do I want to use? Okay. What if I started with something like this? And I asked simply, where does it come from? What did I tweak to get this power series? Now, I can't use anything from a Taylor series expansion that I know, because that we start with a function and we generate the power series. Here, I'm starting with a power series and asking, did this come from a specific function? Now, all of the series that we started working with were just series. They didn't represent any particular function. We know that if we start with a function and we do a Taylor series, we take the derivatives, find the coefficients, we can generate a power series for every specific function. But every time we write a power series, it didn't necessarily come from a specific function. It's just a random arbitrary sum. I'm asking, what function generated this? So I'm telling you it does come from somewhere. So how the heck are we supposed to figure it out? Well, there are a few clues, because we know the nature of the e to the x. We know the nature of sine and cosine, particularly think of the factorial terms. We know the nature of the geometric. So with an n factorial right here, does anybody want to make a guess? Which function do you think this most looks like? Anybody? Not the final answer, just which function. Sine x, cos x, e to the x, geometric.
I want to say e to the x, but
why? Keep going.
Because of the x to the n over n factorial.
It's really that guy right there, because we know with sines and cosines, there's a 2n factorial. And we know with the geometric, there's no factorial. So you're right. This is probably something to do with an e to the x kind of thing. Now, it's not necessarily e to the x, but it's definitely exponential because of that guy. That's sort of the giveaway. So what I need to do is figure out how to rewrite this. Well, I have a -1 to the n, and I have a 3 to the n. I have -1 to the n, I have 3 to the n, and technically right here, isn't that x to the n times x to the 4? Does everyone see that? What can I do with this guy? I can put it in front, because that's one of the tweakages. Now, what else do we have? I have a -1 to the n, a 3 to the n, an x to the n. Isn't that the same as -3x raised to the n? Is that the same thing? Simple rule of exponents. So now I would have this is the form of power series. This is not the form of a power series. The form of a power series, x to a power, is isolated, but I'm working backwards. Now, Lisi says x to a power. Well, that sure looks like what I need, because isn't it e to the thing equals the sum of 1 over n factorial thing to the n? Don't we know this? We know this. Well, there's my thing. So I think we can say this is x to the 4th times what?
E to the -3x, or 1 over.
No, keep going. E to the
Negative 3x.
That's it. You're done. Perfect. Oh. Now, if we worked backwards, the way I started, I said, okay, let's start with this and let's tweak it. You all would have got something that looks like that because the route you took would have been the, one step at a time. You'd have said, well, let me go from here to here to here. That's all correct. Now, if I just write down a random power series, it does not necessarily coincide with a very specific function, but those factorials are kind of a giveaway. So we want to do a couple of these. So the question is, what function does this equal? And you just said it's equal to this. Now, what about things like interval of convergence? Well, we know the exponential converges for all real numbers. We know sine and cosine converge for all real numbers. We know the geometric only converges when the absolute value of r is less than 1. So the geometric is probably the only one where I have to worry about things like convergence. But this is nice. So let's try another one. Oh, let's try a few more actually. Dropping things here. How about we do one like this? This one looks, oh yeah, this looks nice and evil. Love evil series. They're so much more fun. And let's probably look at it. You can see it. All righty. Now, I don't want the answer because we didn't give the answer in the last problem. We said, hey, it looks like an e to the x kind of thing. So what basic function does this one look most like? Anybody want to try?
Cos x.
Now, why cosine?
Because of the 2n factorial.
Beautiful. What if that had been 2n plus 1?
Sine.
Then it would have said exactly. And it's really difficult to manipulate factorials. Okay, if you said, well, can I make this look like the sine? Yeah, but I'd have to multiply top and bottom by 2n plus. I'd have to do stuff that would make it really icky. So let's remind ourselves, what is the power series for the cosine? Because what are we comparing this to? What are we going to try to make this look like? Okay. So again, the most important part is cosine of thing. Therefore, would be, I like using formal mathematics whenever possible, thing to the 2n. So if we've decided that this is a cosine, and by the way, the negative 1 to the n and the 2n factorial make it a perfect fit, then I need to make this become my thing. Is everybody cool with that? So that means I need to write both of these with an exponent of 2n. Well, I think the -3, I can do something with that. I think we all know that x to the 4n minus 3 is just x to the 4n over x to the third. So I can take this guy and pull him right out. So let's do that. So how about if I put this in front? Okay, I don't need this anymore. So if I put that in front, now I need to make the other guys look like something to the 2n. Well, x to the 4n, how do I make that look like something to the 2n?
X squared to the 2n.
Beautiful. Everybody cool with that? So definitely I'm going to have an x squared to the 2n. What about 4 to the n?
You basically do the same thing, 2 squared to the n, or 2 to the 2n.
Okay, let's do it in baby steps. Does everyone agree? 4 to the n is 2 to the 2n. X to the 4n is x squared to the 2n. So can I write this then, without wasting any time, as 2x squared to the 2n? Now double check, right? A product to a power, each term in the product. So 2 to the 2n, okay. X squared to the 2n, and then over 3. Okay, so we're good with this, everybody? Can we now translate directly to our answer? Well, what is this here? Exactly. Because I have -1 to the n over 2n factorial thing to the 2n. So what's this part right here?
Cosine of 2x squared.
Cosine of 2x squared. You did all the heavy lifting already. And what about this? Right there. Beautiful. Now this will converge for all real numbers, except what? Because cosine, the interval of convergence, is all real numbers. Will this converge for all real numbers? What do you think?
X can't be 0.
Yeah, it'll converge for all real numbers except 0. So basically, you would converge for all positive numbers, or you'd converge for all negative numbers. So that's how you generally do something like this. Your interval of convergence is generally just one interval, not a union of intervals. And what you do is, if I have initial conditions that give me positive or negative x values, then that's how I know which interval. You don't decide, you would just say it converges either for all positives or all negatives. But 0 is not defined, but that's okay. Let's do one more of these. Probably the hardest one of all. We'll save that one for last. How about oy vey, this one looks nasty. Now, is this exponential, sine, or cosine? Is it any of those three? Anybody want to try that one? Is it any of those three? It's a yes or no. Not a
No.
no. Why not? What's missing?
No factorial.
No factorials. So what does that really leave us with? What's the only form left that we have to consider? That's a general form that we know really well.
Geometric.
Geometric. So let's remind ourselves what geometric. 1 over 1 minus, I'll use x. That's n equals 0 to infinity of x to the n. Okay, we know this. All right. We know this as long as the absolute value of x is less than 1. We forget because we usually write an r here. Okay. Well, is this of that form? Well, yeah, sort of. Oh, you know what? I have things raised to the nth power, so I can certainly manipulate it. So again, our more general way of saying it is if it's 1 minus thing, then it's the sum of thing to the n. So what I need to do is make all of this look like something raised to the nth power. Well, obviously I have extra stuff right there. So why don't we deal with that? I have x, whoops, I have x to the 3n plus 2. That's clearly x to the 3n times x squared. And then I can think of this, if you will, as x cubed to the n times x squared. So I'm going to move the x squared to the outside. Now we're not there yet. That'd be a lot easier if this was 2 to the n, because then I could put it inside. So I've got 1 over 2 to the n minus 1. Can I say this equals 2 over 2 to the n? Is that legal? What do you
Legal.
think? That's cool. So how about if I write that as 2 times 1/2 to the n? So far, so good. So that's 2 things out of the way. And then lastly, of course, I have the negative 1 to the n. Well, that's the easiest one of all to deal with. So at this point, that 2 right there, I'm going to move in front. So now what I've got is negative 1 to the n, 1/2 to the n, x cubed to the n. That's what we have so far. That's what we just broke it down. So clearly I can write that as one thing. So we're almost there. So 2x squared. So how about negative 1/2 x cubed to the n? So is everybody okay so far? Well, we're good with this? It took a little bit of work, but this quantity right here is identically equal to this quantity right here. And this is the form of a geometric series. So we can say this is 2x squared times 1 over 1 minus, there's our r. Now we'll put the restriction on last. In other words, X is, absolute value of X less than something is going to show up somewhere along the line. Well, I've got a half on the top and bottom. Or do I? What can I do at this point with this quantity? Help me out, folks. What can I do? Anybody? Multiply maybe? I mean, I'm not quite done yet. So 2 over 2. Well, what will that give me on the bottom? That give me 2 plus x cubed. And what will that give me on top? It'll give me 4x squared. So if we haven't made any mistakes yet, hopefully we haven't made any mistakes yet, I've got this. Now, this is equal to this for all real numbers? Or does this one have restrictions? Anybody want to try that one? Everybody got real quiet on me. Do I have restrictions?
X cannot be the negative cubed root of 2.
So yeah, there's something in there that I gotta, Now, remember the absolute value of R has got to be smaller than 1. I'm not going to get it from that statement. I'm going to get it from that statement, or I'm going to get it from that statement. In other words, the absolute value, that's my R. That's my R. So the absolute value of negative 1/2 x cubed has to be less than 1. Well, the absolute value of negative 1/2 x cubed is the same as 1/2 absolute value of x cubed. So therefore, the absolute value of x cubed has got to be smaller than 2. So the absolute value of x has got to be smaller than the cube root of 2. Aha. So that tells us. So therefore, and the one problem that everybody in Calc 2 always has at this point is separating interval of convergence with radius of convergence. Radius is easier. Interval is parentheses or brackets from one number to another number, everything in between. Radius is just a constant. So when I ask for radius of convergence, a lot of people will just leave their answer like this and say, Mr. Brown, I'm going to let you figure out what the radius is. I'm not really sure. The radius is not an inequality. The radius is not a variable. The radius is a scalar. So in all of this, what's the radius? I think Joshua already said it. What is the radius? It's written on here somewhere.
The cubed root of 2?
It's either that number, or that number, or that number. The radius is the cube root of 2. Meaning as long as I'm within cube root of 2 of the number 0, because this is expanded about 0, it's x minus 0. So this evil looking thing here is equal to this as long as this statement is true. And that's really important. It's only true if this is true. Because if you look at this for a moment, as x grows without bound positively or negatively, this is going to grow without bound. But if this x grows without bound, this is approaching 0. So there's a contradiction there. Oh, that's why I've got to be within cube root of 2. Okay, now we are completely done with everything power series. Now we're going to move on and start talking about conic sections. Now, this part of the sequence has no calculus in it. There's no calculus whatsoever when discussing conic sections. So people say, why do we put them then near the end of Calc 2 if there's no calculus? Well, it's because of the need to understand them in 3 dimensions. We spend a lot of time with conics in 3, and we don't review conics in 3 dimensions in Calc 3. So we throw it in now just to kind of give you a reminder and hope that you don't forget it by the beginning of next semester. It really is that simple. We easily could move this to next semester right before we need it, but we're going to review it anyway. So when we talk about conic sections, there's a few different ways to think about them. And we can think about the pure geometry, first of all, which is a good way to start. So what we do is we say, let's consider a cone. This is technically infinite. Oops. This is technically infinite. That's not dotted there. This will be dotted. Okay, a circular cone, because it has circular cross sections as opposed to different types of cones, and this goes infinite in both directions. So what a conic section is, if I take my big knife, think of this like, gelatin, I can slice through it. If I take my knife, there's a few different ways I can slice this. I can slice it perfectly parallel to the ground. I can slice it at an angle, or I can keep going and slice it through the open top, or keep going and slice it vertically so I actually hit both pieces of the cone. There's actually 4 different ways I could slice it. Imagine that I'm just going to be in one position and I'm just going to keep changing my angle. So the first slice, let's say, is perfectly horizontal. Okay, then what I'm going to get is that ring right there, and that cross section will be a circle. It's not a bad picture. That cross section is a circle. So a circle is a type of conic section, a section of a cone. If I change the angle of this thing, well, it's still going to be round-ish, but it won't be circular anymore. What would that shape be? Anyone? What's that guy? That's the ellipse. So, think of like an elongated circle in a sense. Like not quite like a high school track, because that's not really an ellipse because there's too many straight portions. Now, let's keep going. Now, let's suppose I change the angle severely. So now when I slice it, it's going to go through this open section here. So it's now going to be opened up forever and ever and ever. That one's a little trickier. So when I hit this, remember it's rounded and it stays open. It never comes back around like the other two. What's this cross section? Or I should say, that's a parabola. That's probably the one we spend the most time on, strangely enough. There's a lot of reasons for that. And then finally, if I do a cross section that's vertical, so I'm technically cutting now through both pieces. So I have this piece going this way and this piece going this way simultaneously. And that's probably the trickiest, most confusing of all of them. And that's what? Anybody?
Hyperbola.
Hyperbola. That's the only one left. So what we're going to do is we're going to talk about the parabolas today, ellipses and hyperbolas on Wednesday. We're actually not going to spend any time on a circle, because a circle technically is just a special case of an ellipse. And we'll discuss exactly what the differences between ellipses and circles are. But everything that is true about an ellipse gets passed on to a circle, but it's not in reverse. So think of it like I have all these properties of rectangles. Everything that's true about a rectangle gets passed on to a square, but a square is special. So what's true about a square isn't necessarily true in reverse about a rectangle. So like a square being a special rectangle, a circle is a special ellipse. And so we're going to basically just talk about ellipses. So that's next day. So today we want to talk about the parabola, and everything we're doing today and Wednesday is 2-dimensional. Understand that every conclusion we make, every fact that we discuss, we will then extend into 3 dimensions next semester, and that's a more general viewpoint of things, but the rules are still intact. So what makes something a parabola? Okay, so we're going to define it. A parabola is the set of points on a plane that are equidistant to a fixed point which is called the focus, and a fixed line which is called the directrix. When I say a fixed point and a fixed line, that means that I'm starting with a point and a line that are already in place. Then I start discussing the parabola. So every parabola starts with a fixed point and a fixed line. Now there's 2 ways we study parabolas in mathematics. One way we study it in algebra, I just give you an equation, like y = x squared, and you graph it and you do stuff. And then we use it in business examples to talk about, equilibrium and cost and profit and revenues. And we do all sorts of things with the graphs of parabolas because they're very useful, and the equations of a parabola. but that's the algebra side of a parabola. We're talking about the geometry side of a parabola. So where the heck does the equation even come from in the first place? So let's start with that picture right here. So there's my directrix. And let's say there's my fixed point. So to be a point on the parabola, I can't just pick a random point out here on the plane. I need a point where the distance, let's say, I'll do my best, about there. Now remember, the distance from a point to a line is always the perpendicular. So if I'm holding a point right here and I said, how far is this from the floor? There are an infinite number of line segments that I can draw from the point I'm holding to the floor, infinitely many line segments. But the shortest line segment is the one that is orthogonal or perpendicular to the floor. That's the one where we measure distance. Just because I can draw an infinite number of line segments from this point to the line, that's the only one that means distance. So I want a point where that distance and that distance are exactly the same. And when I do this, when I consider all of the points that make this true, I will actually get a parabola. So for example, if I pick exactly halfway between this point and the line, I go exactly halfway. Okay, that's kind of like the starting point. So as I'm moving out, what I will see is I'm going to get this sort of shape. And most of us are familiar with that. So, in other words, these distances are equal. So I go there, there, and so on. As I'm drawing my line segments, if I did a good job of drawing my parabola, I will find that every point on my parabola is equidistant from the point and from the line. So that's the starting point. Now, this guy that I drew right here, the one that's the closest to both, draw it again. This one right here, that's the closest point to both the line and the focus. Does anyone know what that one's called? It has a very important name. It's the most important point on the parabola, in fact.
The vertex?
Well, the vertex. I don't actually see the focus. I don't actually see the directrix. I see the vertex. This one's called the vertex. Okay. Now, there is another invisible line. There's two lines with every parabola. The directrix, and then there's another invisible line that passes through the focus and the vertex. This line is called the axis of symmetry. Some of you may remember doing that in algebra. That helps you draw the graph. If I know where the axis of symmetry is, that means my graph is a mirror image, right? It's going to look the same on both sides. So really, now here's the thing. I've got my parabola. Let's just say this is my parabola. Now let's pick a point on the parabola. Let's call it x comma y. Now, if that's going to be x comma y, then what I need to do is I need a set of x and y axes. And the way we're going to set it up is I'm going to do it in such a way that my x-axis is going to pass through the vertex, which I'm going, oops, that's awful. I'm going to put the vertex at the origin. See, I can put the vertex any place on the XY plane I choose. I'm going to choose to put my vertex at the origin. A lot of you are thinking the directrix should be the x-axis. No, 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 I don't want the directrix to be my x-axis at all. I want the vertex to be right here. Okay. Then if the vertex is right there, then every point on the parabola I can call x comma y, and then I can give a really simple equation. Now, the focus. We're going to say that point is 0, comma p. The distance from 0, 0 to 0, p is a length of p. That's often referred to as the focal length or focal distance. That makes the directrix then the horizontal line y equals negative p. Okay, so if I have a parabola whose vertex is at the origin, and we'll move the vertex, we'll do a shift later, but let's figure out what's the equation of this particular parabola. Okay, it isn't y equal x squared, by the way. So what do I do? Well, let's do two things. Let's establish that distance. For lack of a better name, let's call that D1. And let's find that distance. And let's call that one D2. And then what we'll do is we'll set D1 equal to D2. Well, using nothing more than the distance formula, right? The distance between points, if you remember, it's the sum of the squares of the distances between x and y and then square root. So x, this is 0p. So it's x minus 0 plus y minus p under the square root d2. Now d2 is a little bit easier because this is vertical. I'm going from x comma 0, excuse me, x comma y, sorry, to this line. Well, this distance from x comma y to the x-axis is a distance of exactly y. And now I'm going another p units. So this is simply y plus p. Okay, I don't have to be clever. Again, this is vertical. So that distance is y. There's another p units right there. I want to set these two equal to each other. Now, because I want to get y by itself, I want to write y equals, I'm going to have to square both sides. So if I square both sides and I write d1 squared equals d2 squared, that will make it a little bit easier. Let me erase a little bit of this down here. So d1, when I square it, will simply be x squared plus y minus p squared. d2, when I square, will be y plus p squared. Okay, now all I got to do is multiply this out, gather terms, and solve. Well, the left side is x squared plus y squared minus 2py plus p squared. The right side is y squared plus 2py plus p squared. And very nicely, cancel, cancel. Remember, we wanted to write y equals. So what do I have left? I've got these two terms with y's in them and this term with an x in it. So why don't we send this guy to the other side? Then we'd have x squared equals 4 times p times y, which means that y equals 1 over 4p times x squared. I said it isn't going to be just simply y equal x squared. It's going to be y equals something times x squared. There's a coefficient here. And that coefficient, by the way, is not going to be 1 in general. It can be anything. So we just figured out that if I have my vertex at the origin, then the equation of my parabola is this. That's it. Now, I'd have to know the focus and the directrix in order to know the value of p. So we'll work with all of those pieces in a minute. So the next thing I want to do is I want to move my shape. Now, I'll remind you, you've done this a million times in algebra and in pre-calculus. If you want to shift something, which is what we're going to do next, okay, I'll give you a simple example. If I had the circle, I have a circle of radius r, okay? If I have if this is the x and y axes, we know the equation of this circle is x squared plus y squared equals r squared. We all know that, right? That's baby algebra. But what if I said, no. I don't want the center of the circle to be at the origin. I want the center of the circle to be somewhere else. In fact, the most general case of the circle is, I'm going to call the center h comma k. Oh, well, then this equation won't work anymore. So you guys remember, I hope, hopefully, that if you're doing a shift, we're shifting from 0, 0 to hk. That means that I subtract h from the x coordinate and I subtract k from the y coordinate. And this is the most general form of a circle of radius r centered at hk. We know this from algebra. I'm not proving this today. But the idea is if I shift, I didn't change the shape of the circle. I just took the circle and moved it. So we want to do the same thing now with the parabola. We want to have it not start at the origin, but start at some other place, like maybe h comma k. That's kind of our universal starting point. So now let's suppose, here's my parabola. Same parabola we had a moment ago, but let's say this point here is now h comma k rather than the origin. This is the parabola that goes through the origin. Okay, that has the vertex on the origin. So what did I just do? I just shifted the y and I just shifted the X. Okay, the same rules apply anytime. Horizontal, you always subtract from the X coordinate. Vertical, you always subtract from the Y coordinate. So to be more specific, because this is a function, I'm going to write it in this form. So this is our most generic general form of a parabola that we already know. Yet that's not the form that you did in baby algebra. Well, not yet. It is similar to what you did in baby algebra. So if I know the vertex, that's at HK, I know the value of P, then I can easily find the focus. I can easily find the directrix. That's a fairly simple thing. So I want to work this from every possible point of view. Now in algebra, you guys remember way back in baby algebra, if you had something, you can use f of x notation or you can use y. It really doesn't matter. We know that's the most generic form of a quadratic function. F of x equals or y equals, it doesn't matter. We know this is the generic form of a quadratic function. The A tells me a lot of information. If A is positive, that means it opens upwards. If A is negative, it means it opens downwards. If A is bigger than 1 in size, then we know, think of it like speed. It goes really skinny. If A is a small fraction, then it moves much, much slower. So the coefficient in front of this tells me a lot. And then you remember, hopefully, when you did the complete the square, when you did the complete the square on this, you eventually got this. This is what you did in intermediate algebra. This is what you did in pre-calculus. You took the generic, you completed the square, and you got this. Now I can read the vertex. And again, this coefficient tells me everything about the shape of the parabola. Now that I'm introducing the focus and the directrix, which hopefully you did in your pre-calc anyway, now you realize that coefficient in front of the parabola is 1 over 4p. Whatever the A is, that is 1 over 4p. So whatever the coefficient in front of the x squared is, that tells me everything about the shape, but also tells me where the focus is. It tells me where the directrix, everything. So let's do a problem from beginning to end. I'm going to give you the equation of the parabola. You're going to tell me where everything is. I mean, the focus, the directrix, the vertex, the axis of symmetry, which way it opens. Then I'm going to give you information about the parabola, like the vertex, focus, axis, and then you're going to tell me an equation. Those are really the only two ways to look at a parabola. So if we start with something like this, let's say I'm going to do y equals, how about, let's keep it simple here. Y equals 1/4 x squared minus 2x plus 3. Let's consider this parabola. Now, there's two things you know right off the bat. The parabola opens upwards because this is positive, and the parabola is fairly skinny because this is small. I would like to know where everything else is. Okay. Now, the easiest route to take is find the vertex first, so you can write it in the vertex form, x minus h squared plus k. But how do I find the vertex? Well, there's only two ways. One is to complete the square, and the other is to use the axis of symmetry. So let me remind you of something that you learned, maybe even in remedial algebra. I've got this, and I want to do the complete the square. But you know you can't do a complete the square when your lead coefficient's anything other than a 1. So the first thing you do is you write it as a times x squared plus b over ax, but I don't need the c, so I'm going to put it on the outside. Okay, so I know these are equal. Now, in case you forgot, when you complete the square, okay, just real quick, if I have x plus, so I'll use a different number, x plus t, quantity squared, that's x squared plus 2tx plus t squared. When I complete the square, that's always twice as big as that. So if I had something of the form x squared plus 6x, and I wanted to complete the square, first of all, this would have to be x plus what? Well, it's got to be half of this, so that's got to be a 3. Now, what's going to go here to complete the square? 3 squared. So if I started with x squared plus 6x, I'd need to add 9 to it for it to be a perfect square. That's it. It's actually that simple, well, always. But I have a lead coefficient that's not a 1, so that makes it a little bit trickier. So what I'm going to do is I'm going to add the right thing. So this is going to be x times x, a times x plus what squared? Well, I take half of this. That would be b over 2a. And now here I'm going to put b over 2a quantity squared. Now this is a perfect square. But I just added something. I added a times this. Yikes. Well, that's right now, that's b squared over 4a squared. I added a times this. So I just added b squared over 4a. So we go minus b squared over 4a. And now I'm done with this. I don't even care about this. I just care about this. The form of my parabola tells me that this is of the form x minus negative b over 2a. That means that the axis of symmetry is the line x equals negative b over 2a. You may or may not remember that from algebra. The axis, that vertical line that passes through the focus and the vertex, is always going to be this. And that comes directly from the complete the square. I don't care about the other part because I can just plug this back into the equation to find the y. Way easier. Okay. So if I know that's the axis, then I also know that the vertex is going to be negative b over 2a, and then whatever it is. And then the focus is also going to have the same x coordinate, different y coordinate. Oh, okay. So the axis is extremely practical to find first. So now going back to here, my axis is what? X equals negative b over 2 times a. Okay. 2 over 2 times a fourth, that would be 4. That tells me then that the x coordinate of my vertex is also 4. The vertical line x equal 4 passes through my parabola. Now, how do I find the y? I don't need to complete the square. Just put 4 in here. 1/4 times 4 squared, that's 4. Minus 8, that's negative 5. Plus 3, that's negative 2. No, always check it. So again, 1/4 times 4 squared minus 8 plus 3 is negative 2. I can now say with certainty that my parabola has the following equation. I've just written it in the vertex form that we did a moment ago. If I multiply this out, I should get this. Now I'll actually do it just to prove to you. So that's 1/4 times x squared minus 8x plus 16 minus 2. And that's 1/4 x squared minus 2x plus 4 minus 2. Whoops, did I mess up? I think I did mess up. Oh, plus 3. Yikes, what did I do? 4 minus 8 plus 3. I can't add. This is why we check. That should be a negative. What should that be? That should be a negative 1, I believe. Again, I don't check as a joke. I always check because I make mistakes. Now let's try that. 1/4 plus 4 minus 1, that's 1/4 x squared minus 2x plus 3. And now we're back to the original. So there's the vertex. I messed up the first time. So I have the vertex, I have the axis of symmetry. I still need the focus. I still need the directrix. This is just the check. Now, how do I find the focus in the directrix? Well, I need to find the value of P. I need to know how many units to move from the vertex in order to get to the focus in the directrix. So since this is 1/4P, then I know that P must equal 1. Now, P can be negative. If my parabola points downwards, P is a negative value. P is always the amount that I add to the y coordinate of the vertex. Okay, so if P was a negative number, then I'm going in the other direction. So I can now say that the focus is 4 comma what? I'm going to add 1 to the y coordinate of the vertex. So that's 4, 0. The directrix is a line. It is not a point. It's the line y equals, and now what I'm going to do is I'm going to subtract this from the y coordinate of the vertex. That'd be -2. So that means that's my directrix. I've said everything I could conceivably say about this parabola. So if I wanted to draw a picture of this parabola, it would look something like this. 1, 2, 3, 4. Okay. By the way, it's totally okay to plot points and to figure out your intercepts and things like that. When x is 0, this is going to be 3 units high. Not sure exactly where it crosses the axis, but we could probably figure that out easily enough. When x is 2, that would be 1 minus 4 plus 3. So when x is 2, it's going to cross. So I'm going to get something like this. Something like that. My directrix, there's the line y equal -2. My axis of symmetry, if I want to put it, that's the vertical line x equal 4. And that's, it's not a great picture, but essentially everything we could conceivably say about this parabola is represented right here. I don't need to draw a picture, although sometimes a picture helps. Because what if this parabola were supposed to be upside down? How would I know that? That would have been negative. Okay, so if I have an upside down parabola with a positive coefficient here, that's bad, and vice versa. If I have an upwards opening parabola with a negative lead coefficient, that's bad. It means I got them backwards. So if I give you any equation of a parabola, it should be a fairly short, seamless matter to find all of the information. And a lot of times you're going to have fractional coordinates. That's not a big deal. All right, so let's try another one. Let's suppose, let's make one kind of ugly. Let's suppose I'm going to give you that the focus is, how about at -3, -3, -2, and the directrix is at y equals +3. There can only be one parabola that satisfies this. There cannot be two. Now, have I given you enough information for you to find all the pieces? Actually, I have. There actually is enough information here. But before I get going, I want to take care of something that hopefully is fairly obvious, but I could mess it up if I'm not paying attention. The focus is 1, 2, 3. Okay, the focus is here. You never actually see the focus. And the directrix is 1, 2, 3. The directrix is right here. Now, where must the vertex be? In relation to the focus and the directrix, where's the vertex? Here, here. Anybody?
It'll be between the two of them.
It has to be between the two. Oh, so it's got to be exactly halfway between. How do I find that? Easy, just take the average of the y coordinates. So right now we have enough to know where the vertex is. I know where the vertex is. It's going to be -3, same x coordinate. And what's the average of the y's?
1/2.
1/2. So it's about right here. Beautiful. Now, tell me something about my parabola. Think shape, things like that. Can anybody tell me something about it?
Faces down.
It faces down. Yep. How do you know? By the way, this is why I say draw a rough sketch sometimes. How do you know it faces down?
The focus is below the vertex.
Yeah, the focus is below the vertex and it's also below the directrix. So it has to face down because remember, it's got to be equidistant. Okay, so I gave you enough information for you to find the vertex, but you also have to notice that it points downwards. Is that important? Yes, because that means that P is negative. That is huge that I get that right. Now, what is the value of P? Well, how far did I go from here to here or from here to here? It was 5 from here to here, so didn't I move 5 halves? So P is question mark, 5/2? Is P 5/2?
-5/2.
-5/2, because I said P is the amount you add. So I would add -5/2 to get to here. I'd subtract -5/2 to get to here. Is that important? Yes, because that affects the sign of my final answer. Now here's what I know right now without doing anything else. I know the equation of my parabola is 1/4p x minus x coordinate plus the y coordinate. I know that's the equation of my parabola. And now that we figured out what the value of p is, then 1/4p, that'd be 1/4 times -5/2. 4 times -5/2 would be -10. So do you agree with this? 1/4p is equal to -1/10. So then I can say that the equation of this particular parabola, the best equation, not the only equation. Sorry, there's a square here. This is the best equation. Why is this the best equation? Because I can read all the pertinent information from this equation. This is sometimes referred to as the vertex form. That's kind of a loose description. If you wrote it as y equals ax squared plus bx plus c, if I multiplied that out and gathered terms, that's absolutely correct. But it's not the most useful form because I can read information from this form. It's very similar to equations of lines, if you think about it. If I gave you the equation of a line, let's just say hypothetically, you had something like this. You have, 2x plus 3y equals 12. This is an equation of a line. In fact, this is what's called standard form. I have the x, the y equals constant. This is generally referred to as the standard form of a line. Yet it's not a very useful form. But if I solved for y, that's called the slope-intercept form of the line. And we all agree this is the most useful form because I can read the y-intercept, 0,4. I can read the slope, -2/3. Those are the only two things that are important about a line. So the slope-intercept form of a line, we consider the most useful version, but there's an infinite number of ways I can write the same line. Here's just two of them. There's an infinite number of ways I could write this parabola. That's just the one that's probably most useful. The only other way you would write this parabola is if you distributed, multiplied it out. But in this case, I don't think that's a useful form because you can't tell anything. I'd have to do all the work to get the information back again. So if I give you the equation, can you tell me information? If I give you information, can you tell me the equation? Yeah. Now, what is it about a parabola? Why is a parabola even interesting to us? Well, a parabola has not only the geometric properties, but it's really the three-dimensional version that we're going to spend time on next semester to discuss the importance of it. So I want to give you a few little tidbits about parabolas that you may not have known some of their properties. So we know about this part. We know if you've ever done a business class or optimization in Calc 1, when I, revenue minus cost equals profit. And if I have a function, this is algebra. I have a function where the cost is essentially a linear model and supply and demand is essentially linear, then it means that my profit function is always going to be a quadratic. And then when I draw the graph where it intersects the x-axis, those are my break-even or equilibrium points. Where it peaks out, that's my optimization. These are all really nice, simple facts, but it's an overly simplified example that doesn't really work in real life. In real life, business models are never quadratics. We just do that in math class because they're easy to study, but they're not particularly useful. We study a parabola more for its geometric properties, not because it works great for modeling business problems. So let me give you a simple example. Now, I'm guessing most everybody here at some point has played some form of billiards. Okay, some of you might even be pool sharks, and I don't mean the kind where you splash around and play Jaws music in the background. I mean, you make some money on the side on the weekends. pool hustlers. So anybody who's any form of billiards, if you've ever played, you understand some of the rules and some of the aspects. You know, I'm trying to knock a ball into one of the 6 holes without knocking the cue ball, the white ball in. Now, one of the things though, and now I'm not talking about trick shots. I'm not talking about you put tremendous backspin or you jumping over. You know, if you go into YouTube, you see some pretty crazy videos. I'm just talking, just keep it really simple. I've got a ball, let's say here, and I want to knock it in. And let's say the cue ball is, I don't know, right here. Now, there's a couple of things I can try to do. I can try to angle this just so it clips it just right, or I can try to hit it and make it bounce and come in this way. Okay, those are pretty much the only things that I would have at my disposal. Now, when I play pool, I'm not a very good pool player, partly because of my vision. I can see up close or I can see far. I can't see close and far at the same time. But one thing I've always been really, really good at is any version of a bank shot. Because I can look at this and say, okay, I need to hit it exactly here. And so I'll like, you know, almost mark the ball with, and then I'll come over and then I'll shoot it and, you know, have it hit it just right there and then the ball will go in. Or I'll say, I want to knock it in here, which means that I need to create a deflection where it bounces exactly here. And for me to make it bounce exactly there, then I've got to hit it in a different spot. And I was always really good at the bank shots working because it's pure geometry. So if I think about things logically, whatever, this is simple geometry, whatever angle this comes in at, and again, I said, leave out backspin and things like that. Whatever this angle is here, it has to bounce off. That angle have to be the same. Taking out, again, backspin and you know, humidity and density of the pool table's fuzz, you know, just simple geometry. These angles have to be congruent. I think we all agree that makes perfect sense. That's the simple physics, not the complicated physics. So why am I showing you this? Because parabolas are beautiful things in this regard. You see, now I won't prove this. If you guys want to see this outside of class, I'll be happy to show you, but it takes a really long time to show the algebra. I've got a parabola. And let's just say there's the focus. Now, in my picture, the flatter the parabola, the further away the focus is, by the way. The skinnier the parabola, the closer the focus is. And here's the cool thing. If I say, let's call, you know, let's have an orientation here. Let's keep it really simple. I want this simple orientation. If I said, draw a line segment, let's say to here, if I think of the tangent line at that point, and then I do the same thing here, turns out this is going to go this direction. If I go here, turns out this is going to go this direction. If I went over to here, this is going to go this direction. There's only one point on the entire XY plane that I can do this. From the focus, if I draw a line segment to any point on the parabola, and here's again what I'm saying, I draw that point right to there. Then if I thought of the tangent line, we know how to find tangent lines. And then I look at the angle I made with the tangent line on this side, I have to make the same angle on the other side. It's an absolute that all of the deflections are parallel. Now, this is a really, really cool property. Okay, this is a geometric property that's very easy to show algebraically, although it'd take me a little bit because we'd have to find the derivative, then the equation of the tangent line in general, then measure the angles. There's a little bit of work involved. But let's suppose that I've got all of this stuff. Hang on a second. Okay, I don't want my phone ringing endlessly. So with this set, so that's very interesting. Okay, so now here's the big thing. What if, okay, I'm going to create a shape that you're going to study a lot next semester. It's called a circular paraboloid. It basically is. It's a three-dimensional parabola. It's a parabola that if I rotate it, looks circular. Okay, all the cross sections this way would be circles, but it's parabolic. From every way I could look at this vertically, it looks like a parabola. So it's called a paraboloid. That means parabola-like. This is one of the simplest shapes that we study, and this is a really important shape. So what I want to do is take my same picture, now imagine that I've rotated it. So instead of just being a parabola, it's three-dimensional in nature, almost like a bowl in a sense. Now there's still a three-dimensional focus, and it would still sit at the same place, but now it's three-dimensional. So now when I do this, I can come in any direction and I still have the same thing. So I got an idea. We might be able to market this. What if I put a light source right here? A little light bulb, something like that. What if I put a light source where that parabola, where that focus is? I can have a finite. This doesn't have to be infinite. I could just cut it off here. If I put a light source there, everybody understand, because of the way it deflects, I would create a narrow beam of light. If you're walking around with a candlestick or a torch, your light just goes in every direction and diffuses. So at a distance, all you see is just a little ball of light. But what if I put that torch where the focus is? I would actually create a beam of light. Think about that. That would be so cool. We could, okay, don't tell anybody. We could invent something that you could hold in your hand and maybe go outside at night and shine a beam. We could put them on the fronts of cars and we could drive at night. Heck, we could have them at malls, really big ones, and point them at the sky and call Batman or whatever. Or has somebody already done this, by the way? Has somebody already done this? Let me see.
Hey, you didn't tell your students last semester about this, did you?
I may have. Oh, I don't seem to have one. Oh, darn. Somebody told me that somebody beat us to it. Those handheld things, they call them flashlights. See, if you unscrew the tip of a flashlight and you look at it, you know what it is? If you've ever had to change the headlights on your car, do you know what they are? And those things that we call Batman at night, yeah, same thing. Yeah, I made the mistake of telling my students last semester, and I think somebody invented it, and now they're making bazillions of dollars. Everything on planet Earth that shines a narrow beam of light is a parabola. Because it would be impossible to have a narrow beam otherwise. The narrow beam of light comes from putting the bulb. So if anybody later on, go unscrew the tip of your flashlight and look at the shape of it. You go, oh my gosh, it's parabolic. And where the bulb is exactly where the three-dimensional focus is. Now, by the way, this is an extremely practical use of a parabola, but it is not nearly the only one. Okay. One of my favorite ones, let me grab one. This is one of my favorite uses of a parabola. Now, you guys are going to do this later, but I put a timer on for 5 minutes because you will get lost and days will pass and you won't stop. See, when you look at a spoon, you start looking at it head on and stuff, you realize the dip and some of the very natures of a spoon, it is somewhat parabolic in nature. And therefore, there must be a three-dimensional focus. So when I put my finger and I poke my finger towards the center, you can't really see it from where you are. I have a reflection of my finger. And then when I get to a certain point, it turns upside down. And then at a certain point, and there's a point right where the tip of my finger is, where all of a sudden the reflection blows up. And I'm not joking, it becomes infinitely large. Finger, upside down, right side up, infinitely large. Like I said, 5 minutes, you could do this all day. There's a point in space where my finger changes from right side up to upside down. And at that point, it's infinitely large. That's the three-dimensional focus of this somewhat parabolic shape. You didn't know that about spoons. Now, that's not the only one. That's not even the one that's used the most often. Okay. Has anybody in this class, you say it out loud, ever been to the Reuben H. Fleet Space Center? Balboa Park. Has anybody ever been there?
Yeah, I've been there.
I used to go all the time.
Maybe it was as kids. That was this typical second grade field trip. I was parent helper many, many times on that field trip. Okay. there's a place in there, second grade field trip, parent helpers, it was always kind of taxing and exhausting, but all sorts of cool things, things floating around. But there's a particular spot in the Reuben H. Fleet Space Center where maybe Joshua and I we're trying to get something together, get rid of the kids. Let's go grab an IPA or something. But he's on the other side of the room. So I said, go stand right over there. So he stands over there and I'm whispering. Can't even remember, 50 feet, maybe 75 feet away. I'm like, all right, Joshua, after class, let's head over and grab an IPA. Okay. And he can hear me perfectly. Now I take one step to the right or one step to the left or one step forward. He does the same thing. And I can yell at the top of my lungs. He can't hear me because of all the kids running around screaming and yelling. So I go back to the same spot and I can whisper. Now, say out loud, how many know which spot I'm talking about? You've actually been there, done that. It would be a shame if you haven't, especially if you've been there. There is a spot that if both people stand at the right spot, you can literally whisper and hear the other person perfectly loud. There's no amplifiers. There's no microphones. Because they created a parabolic backdrop on both spots and you're standing right at the focus. And the sound wave is amplified as a result. And you can hear each other perfectly. And by the way, you've seen uses of these. If you've ever watched a football game, let's say a professional football game, like a Monday night game or something, they'll have the guy standing on the sidelines. He's got the big cone-like thing, and he'll be pointing it at different players during the course of the game. And it always seems right when he points it to somebody, that's when they swear. I don't know why, it's like clockwork. But he'll be pointing at it and you can hear the conversations because it's parabolic in nature, and that's what they're doing. They're focusing kind of like the beam of light, but it's really incredible. So police, when they're sweeping certain neighborhoods in their vans, will point the same thing at the households and they can hear the conversations inside. They don't have microphones inside. They're picking up the sound waves. They're picking up the sound waves and channeling them. It's pretty amazing science, but it's actually not that complicated. Okay. But the coolest thing, and this is to me the greatest use of parabolas ever. My honeymoon, which was almost 30 years ago, it'll be a few more months, it'll be 30 years. My wife and I went to Cancun. We spent one day on a tour to the ancient Mayan ruins of Chichen Itza. I don't know, has anybody ever heard of Chichen Itza or been there? Just say it out loud if you have. I'm curious. Because every class I've ever taught, there's always somebody who's been there. Okay, there's ancient Mayan ruins that they had only been recently uncovering. It was a really long rickety bus ride to get there. These ancient ruins, I mean, they had unearthed a pyramid, a gigantic pyramid that I got to climb up, and my wife took a picture of me. I understood only a few years later they stopped letting tourists do that because they were finding it was, things were starting to crumble and decay. They were unearthing entire buildings that this is like 3,000 years old. But the coolest thing is they unearthed essentially what was a soccer stadium. It was huge, this huge stadium, and vertical walls. And the walls were very, very high. And it was where the spectators sat. And there were these things that looked like basketball hoops, but they were really high off the ground. I can't remember, 20 or 30 feet off the ground. And it was a fairly fat ground. And, if you're looking at the architecture, you're saying 3,000 years old. How did they build this stuff? It was pretty incredible. How did they build this pyramid? It was amazing. But that wasn't the coolest part. So the tour guide is having us walk. And by the way, this particular stadium, this is where they had quote unquote soccer games. That's what they called them. Soccer's been around for a really long time, and soccer balls hadn't been invented yet for a few thousand years. So they played games of soccer, but they didn't use soccer balls. Anybody know what they used? This is traditional in most cultures going back. Anybody want to guess what they used for soccer balls?
Rocks.
No, the head of the deposed clan leader that they just overthrown. Generally, they used heads. Then they might put it in a bag, but they use heads. Yeah, I mean, if you watch any old movies, that's not actually unusual. It's kind of creepy though. But they would have these massive soccer games, thousands of people in the stands, and they'd have one person in there addressing the crowd. Again, this is 3,000 years old. So the tour guide had us walking. He says, "Okay, well, as you're walking, clap." Yeah, we're on the floor. We're clapping. Okay. And you got to a point and you clapped, and the vibration of the sound almost hurt your ears. Like, whoa, and you back up a step, nothing. Go forward a step, nothing. Stand in the right spot. You clap. The reverberation and the vibration, it was as if somebody was just, pounding you with speakers. They figured out a way. There's one spot in the stadium. If you stood, every person in the stadium could hear you perfectly, even if you just talked at a normal voice, and they might be 300 feet away. And there were thousands of them screaming and yelling. There was one spot because, again, kind of like the Rubin H. Fleet Space Center, they created a parabolic situation where if you stood in the right spot, one person could address the entire crowd. Now, the thing I think is so cool about this is not just that somebody figured this out. This was 3,000 years old. They figured out this sort of mathematics. The rest of the world was a little farther behind them. They figured out ways that sound waves can be amplified using parabolas. So we study parabolas because they have so many uses in the architectural and engineering world, but way beyond just the physical shape we think about, because, for example, channeling a light source or channeling sound waves is one of the huge uses of parabolas. And since most of you are going to be engineers, it's kind of useful to know this is why we study parabolas. Now, there's nothing complicated about parabolas. They're actually quite easy to work with and use. And what I showed you today is what I want you to know. Given an equation, can you pick off all the information? Given some information, can you give me back an equation? Now, we're going to do the same thing more or less on Wednesday with ellipses and hyperbolas, but I'm also going to give you some physical meanings of those. They're not just shapes that we study in an algebra class and we don't know why we study them. No, it's really important that you understand why, because of their uses, and because you probably will have to design something at some point that's parabolic in nature. So, hold on, let me stop.